majority of cases, we need more than one bit to perform our computation. For quantum computing, it is also true. So in this lecture, we are going to learn the mathematical description of systems with multiple qubits. So here you see a table for, now imagine that we have two particles, each carrying one qubit, and in this table we have the possible measurement outcomes for these two qubits in our ordinary basis, 0, 1. And we have four possibilities of such measurement here. Now it is convenient for us to describe this system, to describe these measurement outcomes, again in some Hilbert space, in some linear space over the complex numbers. But since we have four different measurement outcomes here, this space has to be four-dimensional. And each measurement outcome will be, again, one of the basis vectors of this space. So let's name these vectors. This measurement outcome we will call 0, 0. This 0, 1. With this 1, 0, and this 1, 1. So we just have named four basis vectors of the space in which we will describe the system with two qubits. Good. Now imagine that one of the qubits have this superposition before the measurement. Can we describe this state before the measurement in the space we just constructed? Yes, we can. We can describe it like this. So we used two of the vectors we just introduced in the previous slide to describe the state of this system. And this system is still in the superposition state, so we can measure it, and the probabilities of the measurement outcomes are still the same. So it's alpha squared for the measurement outcome 0, 0, and beta squared is the measurement outcome for 0, 1, since measurement of the first qubit always gives us 0, and only measurement of the second qubit is probabilistic for us. And again, the sum of the coefficients before the vectors, the basis vectors in the state, gives us 1. So it is a unitary vector. Now let's consider a more complicated situation when both qubits are in some superposition. And we still can describe this state in our newly constructed space like this. And it's easy to show that the sum of squares of all the coefficients here gives us 1, so it is again a unitary vector. And for any state, for example, this one, the probability of obtaining this state after the measurement is alpha delta squared. So we have everything we got used to in the case of one qubit. And this is true because we believe that measurement of two different particles are independent events. So we can multiply the probabilities. We have alpha squared for obtaining this 0, and we have delta squared for obtaining this 1. So the probability of 0, 1 is alpha squared multiplied by delta squared. Okay, now the interesting part is we just constructed the description of two particles, of the state of two particles, like we just did. But the amazing part is that we cannot construct the whole space like this, because there are vectors in this four-dimensional space. For example, this one. Which cannot be constructed through this process, just as I just described. But physically, this state, which is described like this, can exist on two separate particles. We will return to this fact very soon. Now, it's a very common misunderstanding about all this. The real quantum systems, the qubits, they don't situate in some Hilbert spaces, and if we take two of them, they don't initiate some tensor product of these spaces. It is our way of describing them. It is our choice. We decide to describe it as some vectors in Hilbert spaces, and it is convenient for us to describe two qubits in a space of 4 dimensions. We already named our bases. Now we have to show how we enumerate it. We have to decide which column vectors will represent these bases. You remember that we have this 1, 0 column for the vector 0, and this 0, 1 column for the vector 1. And now we have to choose for each basis vector of our newly constructed space which column vectors represent it. And there are many rules we can use for this, and the most basic rule for us will be the following. We just take the two vectors. This one is 0 and this one is 0, so they form this vector 0, 0, and we take a tensor product of this vector, so the Kronecker product. So we have here 1 multiplied by 1, 0, and 0 multiplied by 1, 0. This is our tensor, which is 1, 0, 0, 0 tensor. And we can substitute it with the vector in 4-dimensional space like this. We just remove these brackets inside of the tensor. So this is the way how we are going to construct the columns for our newly defined bases. For example, if we have vector 0, 1, we will have to do the same thing. So 0 is 1, 0 vector multiplied by 0, 1, which is vector 1. And is again, we take this 1 and multiply it by the whole vector here. So it's 0, 1. Now we take this 0 and multiply it again by this vector. So this gives us this tensor, which we can naturally map to this 4-dimensional vector. And of course we can perform this rule, we can apply this rule to all the basis vectors, and we obtain this table. We can choose other rules to enumerate our vectors. But this rule is very convenient because if you may have already noticed that if we use the binary notation here, so we look at these as some numbers this 0, 0 is 0 in binary notation. This is 1 in binary notation. This is 2, and this is 3. So it's numbers of our vectors. And here, when we have this 0, we have 1 on the first place. When we have 1, we have 1 on the second place. Here we have 1 on the third place and on the fourth place. So the position of this single 1 in the column, it is defined by the number of the vector, which we can read from its name in binary notation. So this is why this rule is very convenient. Now, if you consider, for example, the state of 3 qubits like this, and this state will be represented by a vector in 8-dimensional space, so it will be a column with 8 coordinates in it. We can see that this number is 5 in binary notation, so we can easily understand that this single 1 will be on position 6 in the vector. And all other will be zeros. Okay. So, of course, for the systems with multiple qubits, with more qubits than two, if you have, for example, n qubits, we will have vectors in the spaces with number of dimensions 2 in the power n. So, for n equal to 1, we have this 1 qubit, which is the vector in the space with 2 dimensions. With n equal to 2, we have 4 dimensions. N equal to 3, we have 8. N is 10, we have 1024. And if we have like 1000 particles, we have this enormous number of dimensions. So it's like 1024 in the power 100, which is approximately this number. So the state of the system with only 1000 particles is described by this number of complex numbers. This is why Richard Feynman was so optimistic about quantum computing. But you may argue that if you take only 1000 of flipping coins, then the number of outcomes of reading these coins will be the same. It will also be this number of outcomes. But for some reason, nobody builds a computer on these flipping coins. In the next lecture, we are going to understand why.